figures there in the back too. That this material will be appearing in the new revision of the Winkler book, but it thought you ought to have that for your own records. Now we're going to talk about a new subject now, and first thing I'd like to cover is some basic principles of plant physiology dealing with these subjects here: how light intensity, temperature, moisture, leaf age, sink size, and vitus species, how these factors affect photosynthesis. And I think this information will be quite important in helping you explain why you trellis, for example, or helping to explain carbohydrate and nutrition utilization when we go into that in next period. So first thing I'd like to cover is the effect of light intensity on photosynthesis of grapevines. And this is covered in that first slide. Do you have those, Dr. Cook? So on this slide here, I don't think we have to turn out all the lights. You might want to take a few notes. On this slide, we have light intensity here on the horizontal axis and photosynthesis here on the vertical axis. And you can see there's an increase in photosynthesis with an increase in light intensity. These figures here are to be multiplied by 1,000. So we have light intensities going from 0 up to 7,000. And we see that there's a linear increase in light intensity. And there's a linear increase in photosynthesis with an increase in light intensity up to about 4,000 foot candles. There it reaches a maximum, plateaus, and then remains about the same all the way out to about 12,000 or more foot candles. And at this point where photosynthesis reaches its maximum level, this is called the light saturation point. The light saturation point is the amount of light intensity where you reach maximum photosynthesis. And this, in grapevines, is generally 4,000 to 5,000 foot candles. Now, there is another point here that I want to define, and that's the light compensation point. And the light compensation point is the point where there's the amount of light intensity where respiration just equals photosynthesis. And at the light compensation point, if a vine was at the light compensation point, it would neither increase or decrease in weight. It would just maintain or hold its own. So respiration just equals photosynthesis at the light compensation point. Now, if the light intensity goes below the light compensation point, then a vine would actually lose weight. Or if a leaf is below the light compensation point, you can think of it as being parasitic on the vine in that it demands photosynthate to maintain its metabolism. Now, here at Davis, the diurnal increase in light intensity with time during the day. Has everybody gotten this information here? Or I put these references on the board just for your own information. You're not going to be held responsible for these, but these are 5 or 6 references dealing with these factors of light, temperature, moisture, and so forth on photosynthesis. And if any of you are interested in pursuing that further, you can look into these. So the diurnal increase in light intensity during a day here at Davis changes something like this. If you plot time here from 6 a.m. to 6 p.m. and light intensity here, this is now on a clear day, a cloud-free day. You increase from, well, this is 0, and you go up to about 12,000 foot candles. you you're up about 2,000 here, already at 6 a.m. in the morning. You increase at solar noon to about 12,000 foot candles, and then of course it's symmetrical, making a curve something like this. So from about 7 a.m. in the morning till 5 in the afternoon, you're essentially at light saturation or above for leaves that are in direct sunlight. Only for leaves that are in direct sunlight. Now, if they're shaded, they're of course going to be lower. So there's about 10 hours a day that for leaves that are directly exposed to the sun at which they are at light saturation or above. Now, let's keep that on for just a minute. I might say that that the primary purpose of trellising then is to keep as many of your leaves at this light saturation point or above. And this is really the main objective of trellising, is to display and keep as many of your leaves above the light saturation point. Because you can see as soon as you're falling down into here, you've when at 1,000 foot candles or less, you're already photosynthesizing at 1/3 to 1/2 the rate that you would be at if you're at light saturation or above. So the whole objective of trellising is to, or the main purpose of trellising then, is to keep as many of those leaves above the light saturation point as possible, to keep those leaves photosynthesizing at their maximum rate. Now, let's go to the next slide. The next slide actually shows you some actual data of a couple of different varieties, plotting light intensity against photosynthesis. Sultana is the Australian name for Thompson seedless. And you can see when they ran this light intensity against photosynthesis using an infrared CO2 analyzer, which actually measures the uptake of CO2, they found a light saturation of about 5,000 for the Sultana field vines, and for the Shiraz field vine, again, about 5,000 foot candles was the light saturation point. For the Sultana shade house vine, or greenhouse vine, it was actually reaching saturation at about 3,000 foot candles. So shade vines, so-called shade vines, or shade leaves, vines growing under lower light intensities, reach light saturation at a lower light intensity. And I think we can interpret this to mean, too, that leaves that are in the interior parts of vine growing mostly in the shade would actually reach their light saturation perhaps at a lower light intensity than those leaves are on the outside of the canopy and growing in the full sun. Now, the next slide will show us how the light that hits a leaf is absorbed by the outside canopy of a leaf. In other words, we're taking an example here where we have 10,000, say we have 10,000 foot candles of light hitting an outside layer or canopy of leaves. That leaf will absorb about 90% of the incident radiation. Only 10% of the radiation will pass through a mature leaf. So if you have a leaf here, and the sun's hitting that, only about 10% of the light will pass through that leaf. 90% of the radiation is absorbed. So if we have 10,000 foot candles hitting this leaf, only 10% of the light is passing through, so you're already down to 1,000 foot candles. And if it has to go through a second layer of leaves, another 90% is absorbed, so you're already down to 100 foot candles. So this means that if you have leaves in the interior part of the vine, and that light has to go through 2 layers of leaves, you're already down to about the light compensation point. And it's even a little bit worse because the type of light that passes through a leaf is mainly the green light. And green light is of lower light quality. In other words, the most active radiation for photosynthesis is the red and blue light, and green light is actually less efficient for photosynthesis. So if these interior leaves on a vine if the light has to go through several layers of leaves, you're at a very low light intensity, and the light quality is also quite poor. You had a question here?
Yeah, what temperature would correspond to 10,000 foot candles?
Well, we're going to cover that in just a minute, but on that first slide there, this was done under optimum temperatures of 25 degrees centigrade, 77 degrees Fahrenheit. Every other thing, the light intensity was the only thing that was limiting in those slides. Moisture and temperature were optimal.
But I mean, for the field light in that.
Well, it'll vary. It'll vary with the day. Like you go out there now, you'll be 5,000, 6,000, 7,000 foot candles, and the temperatures are what, in the 70s. So it'll vary with the day. Now, so you can see then if you're going through one layer of leaves, you're already down to 1,000 foot candles. And going back to that previous slide there, at 1,000 foot candles, the vines are already only photosynthesizing at about 1/4 their maximum rate. So again, emphasize that the primary purpose of trellising is to get as many of those leaves out in the full sun as possible so that they're working at their maximum rate. Now, the next slide illustrates the light distribution pattern within a canopy, a canopy here at Davis. This happened to be a black corneth vine that was trellised on a single wire. Black corneth and it illustrates what kind of type of light intensity you can have in the interior part of a vine under a very dense canopy situation. What we did is go out at noontime and measure with a light measuring instrument the light intensity at 1 foot intervals. This being the trunk here, we measured light intensity at 1 foot intervals and at 1 foot intervals here with elevation. So you can see that there are essentially only two light levels within this canopy. There's a very high light intensity on the outside periphery of this vine. Again, these numbers have to be multiplied by 10 to get them in foot candles. So if we go across here, we see that we have 10,000 foot candles. And immediately when we get inside that canopy, we're down to 800, 250, 80, 80, 60, 900, and back to 9,000 foot candles. So really what this indicates that with this type of trellising system with a single wire and a very dense canopy, there were really only two levels of light intensity, very high light intensity on these outer periphery of leaves, and a very low light intensity in the interior part of the vine. In fact, here in the very center of the vine, you can see we're down below the light compensation point. And an important clue on a vine when you look into the inside a canopy with this kind of light intensity, if you're very low at very low light intensities, usually the leaves will tend to be yellowish, and they'll be senescing, and they'll be tending to fall off the leaves at a very young stage if you're at very low light intensities. So when you look in, you see if you have a vine and you open up and look under that canopy and you see a lot of yellowing leaves tending to senesce early, usually you can be pretty sure that the light intensity is very low and even below the light compensation point. See, a leaf will tend to senesce and fall off if that light intensity is below the light compensation point. It has a mechanism of rather than remaining a parasite on that vine, it will tend to senesce and fall off rather than being a drain on the vine. A question?
Would you be better off in this, even if they weren't senescing, if you went in and pulled the leaves off in the interior of the
No, I don't think so. They're not really much of a parasite, because we've done some labeling experiments to see how much they take away from the other part of the vines, how much are imported from other leaves, and it's very, very small. But they're not, at the same time, they're not contributing nothing to the other part of the vine. So it certainly would not pay to go in there and pull them off, because they're not. If they are a parasite, they're a very, very weak parasite. But the main point is, those leaves are capable of photosynthesizing at their maximum level if they do get light intensity, and you can increase that considerably if you design a proper trellising system. Now, it's not quite as bad as what we're making out here either, because there is the so-called sun flecks that are occurring all the time. And these are light, flecks of light that hit a leaf or a portion of a leaf for an instant. And it's been found that if 1% of the leaf area receives light at light saturation, it's enough to maintain, it's enough to more than compensate for its light compensation, to remain in respiration and maintain its above the light compensation point. So if only 1% of that leaf is receiving light intensity above the light saturation point, it will it will photosynthesize more than it will respire. And in fact, it's noted in another experiment that Quietemann did here, where he only had 8% of the leaf surface at light saturation. It was equivalent to another leaf that it photosynthesized as if 25% of that leaf area was at light saturation or above. So a leaf has a mechanism where it can efficiently utilize light if only a portion of that leaf receives light at light saturation. Now let's go on now and talk about the let's turn the slides off for a minute. Now we'll talk about photosynthesis. Talk about temperature effects on photosynthesis. And you have in your handout this type of curve here, and I don't have a slide of this, but you have it on your handout, the effect of leaf temperature on photosynthesis. And we have temperatures here ranging from 50 up to 114 degrees Fahrenheit, and photosynthesis plotted on this axis. And you see that the maximum rate of photosynthesis is reached at about 77 to 86 degrees Fahrenheit, corresponding to 25 to 30 degrees centigrade. And then there's a very sharp decrease in photosynthesis when you go above 90 degrees, and time you're up to 104 to 114, you're indeed at a very low rate of photosynthesis. Question?
Yeah, how does this leaf temperature compare with the ambient temperature?
Leaf temperature, if it's in the direct sun, will be anywhere from 5 to 18 degrees Fahrenheit above the ambient temperature, depending on the angle that if the sun's hitting it at a direct right angle on a warm day, we've measured as much as 10 degrees centigrade or 18 degrees Fahrenheit higher leaf temperature than ambient temperature. A leaf that's in the shade will tend to be almost at the ambient temperature. So we see that there is a marked temperature, photosynthetic response to temperature, reaching a maximum at 77 to 86 degrees Fahrenheit, and a decrease on either side of this temperature. Now, the mechanism of why photosynthesis decreases when you get above 86 degrees Fahrenheit is that generally the enzymes are responsible for fixing the CO2 into carbohydrates reach their optimum at about 86 degrees Fahrenheit. And then they're decreased, their enzyme activity is decreasing above this temperature, and the enzymes responsible for respiring still have not reached their optimum. They can increase all the way up to nearly 45 degrees centigrade, up to 114 degrees Fahrenheit. So the enzymes that respire off or account for respiration, breaking down the carbohydrates to CO2 and water, they continue to increase, while those enzymes responsible for photosynthesizing are already above their optimum and are decreasing. And secondly, when the leaves reach above 90 degrees or so Fahrenheit, they tend to be under moisture stress, and the stomatas tend to close somewhat. So there's also high temperatures will tend to close the stomatas, and this also will increase leaf resistance and decrease photosynthesis. One question?
Dr. Kliewer, might just remind them that this is the big weakness in the degree days.
Yes.
All the degrees in their present system count equally.
Yeah, exactly. So, yes, the degree day systems accounts every degree above 50 degrees is equal, and so this vividly shows why a weakness in the degree day system here. The photosynthesis was, of course, much higher here at 77, 86 degree Fahrenheit than it is up here at 104 or down here at 50 or even 68. So we very much need a modification in degree day system where we can perhaps apply factors. Maybe we should go through and divide degree day systems into temperature classes of 50 to 60, 60 to 70, 70 to 80, 80 to 90, and maybe put one of these as is equal to 1, and then every other temperature as a proportion of that. For example, if we assigned 75 to 80 degrees, 75 to 85 degrees Fahrenheit as 1, then everything as a factor of that. This would be a much better system. Well, I think we better stop there. And one question here? Any variety? This has been checked on several varieties, and every variety has reached their optimum between 77 and 86 degrees Fahrenheit.